It all began with the launch. The moment a fragile machine with incredible precision set out on a journey no one had ever attempted before. Voyager 2 was not just any spacecraft. It was humanity's first envoy to the outer planets, a silent observer tasked with uncovering the secrets of worlds we could barely imagine. Its trajectory took it past gas giants and icy moons, revealing environments that seemed practically alien in their strangeness. The data sent back to Earth forever changed our understanding of these distant worlds. Voyager revealed Jupiter's raging storms, Saturn's intricate rings, and Neptune's supersonic winds. But it was the brief encounter with Uranus, the least studied of the giants, that left us with the most enigmatic mysteries, secrets hidden in the planet's magnetic field, its moons, and its strange lopsided tilt. Voyager's journey may have concluded decades ago, but its discoveries still resonate with the questions we ask today. And today, by revisiting its data with modern technology and fresh perspectives, we're uncovering things about these worlds, namely Uranus, that Voyager itself could never have imagined. The flyby over Uranus performed by NASA's Voyager 2 spacecraft in 1986 was a milestone in our exploration of the outer solar system. For the first time, we had the chance to closely observe this distant, mysterious planet. Its blue-green hue, faint rings, and tilt so unique that Uranus rotates around the sun like a rolling ball. However, beneath the stunning images and data gathered during this encounter are findings that suggest the understanding we gained from Voyager's observations, particularly of its magnetosphere, may need to be revisited. The journey of Voyager 2 to Uranus occurred under atypical conditions. The spacecraft arrived just days after a rare and intense burst of solar wind, a high-energy surge of charged particles from the sun that compressed the planet's magnetic field to a fraction of its normal size. Solar wind, a constant stream of charged particles from the sun, usually shapes planetary magnetic environments, creating magnetospheres that shield worlds from harmful solar radiation. But in this case, the solar wind's intensity was so high that it compressed Uranus's magnetosphere to about 20% of its usual volume, significantly skewing the data the spacecraft could collect. According to a recent study published in Nature Astronomy, such circumstances are rare, occurring only about 4% of the time. Had Voyager arrived a week earlier, it would have observed a much larger magnetosphere, more in line with those of other giant planets like Jupiter, Saturn, and Neptune. Previously, scientists believed that Uranus's magnetosphere was unusually weak, with low plasma concentration and highly energetic radiation belts. Plasma, a state of matter where atoms split into charged particles, is a common feature of other planets' magnetospheres, particularly those with strong magnetic fields. Voyager's data suggests that Uranus's magnetosphere lacked plasma from the solar wind and its moons, leaving its plasma environment abnormally sparse. However, new analysis points to a different conclusion. The solar wind likely suppressed plasma presence in the planet's magnetosphere, leading to the mistaken belief that Uranus was devoid of a significant plasma. By reassessing the data in light of the solar wind's unusual intensity, scientists have uncovered an error in interpretation. They now believe that Uranus's magnetosphere is more akin to those of other giant planets than previously thought. Additionally, this research has changed our understanding of Uranus's moons, Titania and Oberon. Previous Voyager observations indicated that these moons orbit outside the planet's magnetosphere, Researchers now suggest these moons are likely within the protective bubble of the magnetosphere, which could have significant implications for understanding the potential subsurface oceans on these moons. A growing area of interest as scientists continue to explore the possibility of life in the outer solar system. And now let's take a closer look at what we know about solar wind. When these charged particles interact with a planet's magnetic field, they exert pressure that can compress, expand, or even reshape the magnetosphere. This interaction is not static. The conditions of the solar wind are constantly changing under the influence of factors like solar activity and the planet's distance from the Sun. On planets with strong magnetic fields, such as Earth, Jupiter, and Saturn, the solar wind can significantly influence their magnetospheres, creating protective shields that guard the planet from harmful radiation. The magnetosphere is essentially a planet's defense system shaped by its internal magnetic field. It acts as a shield, deflecting and redirecting charged particles. However, the system is not impervious. The strength and size of the magnetosphere depend largely on the dynamic pressure of the solar wind, which varies in intensity and velocity. At the time when Voyager 2 completed a flyby of Uranus in 1986, conditions were extreme, as the dynamic pressure of the solar wind was at its peak. The dynamic pressure of the solar wind is the product of the solar wind's mass density and the square of its velocity. Under normal conditions, Uranus's magnetosphere extends about 22 to 25 planetary radii from the planet. However, during the flyby, the magnetopause, which is the boundary where solar wind pressure balances the planet's magnetic pressure, was compressed to 17.3 RU. As solar wind pressure increased in the days leading up to the flyby, the size of the magnetosphere decreased significantly. This compression not only affected the magnetopause, but also likely influenced the unusual behavior of the planet's radiation belts. Typically, radiation belts around planets are formed from plasma sourced from the planet's atmosphere, moons, and the solar wind. The intense solar wind during Voyager's approach likely pushed plasma out of Uranus's magnetosphere, leaving the region depleted and altering the typical behavior of its radiation belts. As a result, an unexpectedly intense belt of electron radiation appeared, puzzling scientists for decades until new findings emerged in October of this year. So, what do we know? The unique nature of Uranus revealed during Voyager 2's flyby has long puzzled scientists. The spacecraft data indicated an unusually tilted and offset magnetic field, contributing to the perception of Uranus's magnetosphere as extreme and unlike any other in the solar system. However, studies have shown that this interpretation does not fully reflect the true dynamics of the planet's cosmic environment. Compressing magnetospheres like what was observed at Uranus are not static changes. They initiate a cascade of dynamic processes. The increase in solar wind dynamic pressure led to the injection of hot plasma from the magnetotail into the inner magnetosphere. This process is similar to what's been observed on other planets such as Saturn, where solar wind compression events amplify kilometric radiation and cause magnetic field reconfigurations. For Uranus, the result was a more intense electron radiation belt and changes in the plasma composition of its magnetosphere. Interestingly, the intense solar wind conditions likely caused Uranus's magnetosphere to behave similarly to those of other giant planets like Jupiter and Saturn. As the magnetosphere compressed, the radiation belts may have become more charged, similar to what occurs during geomagnetic storms on Earth. This phenomenon is well documented on Saturn, where magnetospheric compression increases electron radiation. On Uranus, an event like that could have intensified electron flux in the radiation belts, even though the planet's environment was previously thought to be nearly devoid of plasma. Increased radiation during this compression event may have also triggered changes in the magnetotail dynamics, such as magnetic reconnection. This well-known process, observed on planets like Earth and Saturn, could have ejected plasma from the magnetotail into the inner magnetosphere, further altering plasma density and radiation levels. For instance, similar events on Saturn have been linked to enhanced radiation belts and intensified auroral emissions. However, the dynamics of Uranus's magnetosphere under these extreme solar wind conditions were not entirely predictable. While we've got a fair amount of data about how magnetospheres behave under compression on other planets, Uranus's highly tilted magnetic axis and skewed magnetic field complicate these interactions. Uranus's tilt may create unique magnetospheric configurations, potentially contributing to the observed intensification of electron flux and the unusual behavior of its radiation belts. Now that scientists have revisited the dynamics of Uranus's magnetosphere, understanding how these conditions affect the possibility of subsurface oceans on the planet's moons has become crucial. The outer moons of Uranus, namely Titania and Oberon, have always intrigued researchers, especially regarding the potential existence of subsurface oceans. These moons orbit Uranus at distances of 17 and 22.8 Uranian radii, respectively, placing them in a unique position relative to the planet's magnetosphere. For the moons located within the magnetosphere, such as Miranda, Ariel, and Umbriel, any subsurface oceans are more likely to be detected through magnetic induction, as the planet's magnetic field would generate currents in the moon's conductive layers, producing measurable responses. However, Titania and Oberon present a different challenge. Positioned near or just beyond the magnetopause, the boundary between Uranus's magnetic influence and the surrounding solar wind, these moons are less likely to experience the same level of magnetic interaction. Earlier studies suggested that Titania and Oberon might remain outside the magnetosphere for significant portions of their orbits. This would hinder the detection of any subsurface oceans, as these moons would be exposed to the solar wind and the magnetosheath, a turbulent region between the magnetosphere, making magnetic induction measurements practically impossible. However, new data indicates that Titania and Oberon likely remain within the magnetosphere for most of their orbits. According to simulations, Titania has less than a 4% chance of crossing the magnetopause, while Oberon's probability is slightly higher at about 13%. This means that, contrary to previous assumptions, these moons are generally located within Uranus's protective magnetic bubble. This finding significantly impacts our detection of subsurface oceans. As the moon remains under protection of the magnetosphere for most of their orbits, the potential for magnetic induction becomes much more feasible than previously thought, opening new avenues for exploration. This conclusion also holds important implications for plasma interactions between the moons and the planet's magnetosphere. While the magnetosheath is typically a plasma environment dominated by the solar wind, the moon's orbits within the magnetosphere mean they interact primarily with magnetospheric plasma. This interaction is likely to be far less disruptive to magnetic induction measurements, making it easier for future missions to detect any subsurface oceans. Science is never static. It is a constant process of discovery, refinement, and sometimes correction. The case of Uranus demonstrates how new data can challenge old assumptions, prompting us to rethink what we thought we knew. However, to truly understand this distant planet, we must revisit it with new technologies. A future orbital mission could provide continuous high-resolution data to study the planet, its moons, and its rings in greater detail. As preparations for the future missions to the Uranian system progress, new insights into the positions of Titania and Oberon within the magnetosphere are critical. Besides understanding the dynamics of the solar wind and the variability of the magnetosphere will influence flight trajectories, ensuring spacecraft arrive at optimal times for data collection. Magnetic induction studies, which have proven successful for other icy moons like Europa and Enceladus, can now be applied with greater confidence to Titania and Oberon. A mission specifically targeting these moons could employ magnetic sensors to investigate their internal structures for signs of liquid water presence beneath their icy shells. A mission like that could also fill in the missing pieces of the puzzle, expanding our understanding of icy worlds in the outside solar system. The future of exploration in the outer solar system is taking shape, with established space agencies and emerging space powers prioritizing missions to Uranus and its moons. In 2022, an orbital mission and probe to Uranus were included in NASA's priority list for the 2023 through 2032 Planetary Science Decadal Survey. This decision underscores the growing importance of studying the ice giants, which remain largely unexplored. The proposed spacecraft, plasma environment, radiation structure, and evolution of the Uranian system, or Perseus, is set to launch in February 2031 and reach Uranus by 2043. The spacecraft will focus on studying the planet's plasma, magnetic fields, and heliophysical environment, providing critical insights into the dynamic processes of governing ice giants. The arrival of this mission will mark a pivotal moment in Uranus research. The spacecraft will have a dry mass of approximately 1 ton, and in addition to its primary objectives, will collect data on Uranus's atmosphere and rings. The launch window for this mission is open between 2030 and 2034. China's also entering the field with its Tianwen-4 mission targeting Jupiter and Uranus. Scheduled for launch in 2030, Tianwen-4 will carry 2 spacecraft on a Long March 5 rocket. One probe will head to Jupiter's moon Callisto, while the other will fly by Uranus. This ambitious mission will mark China's first exploration of the ice giants. The spacecraft, thought smaller in mass compared to NASA's mission, will also be equipped with instruments designed to study Uranus's magnetosphere and will venture into the outer solar system using a series of flybys to gain the necessary momentum. The achievements of the Voyager missions in exploring the outer planets have paved the way for future discoveries. But the path to a true understanding of space lies in our endless curiosity and exploration. As we continue to gaze at the stars, their legacy inspires us to embark on new ventures, providing the foundation upon which humanity builds its understanding of the universe. In the vast expanse of space among countless stars and galaxies, there is a whisper, the whisper of a distant star that's traveled light years to reach us here on Earth. This is not a science fiction tale, but a reality of our universe, a testament to the continual growth of our understanding of the cosmos. Scientists eavesdropping on space have detected a signal, a radio wave, from a star system not so different from our own. A star known as YZ Ceti is located just 12 light years away. But it's not just any signal. This signal carries a potential signature of a magnetic field very similar to the one that protects our own planet. The magnetic field that may envelop a rocky Earth-sized exoplanet orbiting YZ Ceti. What could it mean? Could this distant world be more like our own than we've ever imagined? And what could it tell us about the search for life beyond our solar system? Let's go light years across to delve into the mysteries of radio signals in space and explore the magnetic fields of distant worlds. In the boundless silence of space, radio signals can, without guile, be called whispers. But what are these signals, and how do they propagate over such vast distances in space? Radio signals are a type of electromagnetic radiation, just like light, X-rays, or microwaves. They're generated by a variety of sources, from stars and galaxies to artificial satellites and spacecraft. These signals travel at the speed of light, carrying information across vast distances in space. They can tell us about the composition of stars, the presence of planets, and even the origin of the universe itself. But how do we detect these signals? The answer lies in the technology of radio astronomy. Radio telescopes, such as the Very Large Array in New Mexico, or the now-defunct Arecibo University in Puerto Rico, are designed to detect and analyze radio signals from space. They are our ears to the cosmos, listening to the faint whispers of the universe. Once a signal is detected by a radio observatory, it is analyzed using sophisticated algorithms and computer models. These analyses can provide extensive information about the source of the signal, from its location and distance to its physical properties. But radio signals from space are not just a scientific curiosity. They also have practical applications. For example, radio signals from satellites are used for GPS navigation, weather forecasting, and Earth observation. They are an integral part of our modern technological infrastructure. So, the next time you look up at the night sky, remember, there's a whole symphony of signals playing out there, a cosmic conversation, an orchestra that we're just beginning to understand. Let us return to the constellation of Cetus, the sea monster, in which lies a star that whispers to us across light years. Her name is YZ Ceti. YZ Ceti is a red dwarf, smaller and cooler than our Sun. It is located 12 light-years away, a close neighbor on a cosmic scale. But what makes YZ Ceti truly fascinating is not the star itself, but what revolves around it. At least 3 exoplanets are known to orbit around YZ Ceti, the innermost of which, YZ Ceti b, is of particular interest. YZ Ceti b is a rocky, Earth-sized exoplanet that orbits very close to its parent star. In fact, it is so close that its year, the time it takes to make one revolution around YZ Ceti, is only 1.6 Earth days. Recently, using Very Large Array, scientist at Bucknell University, Professor Jackie Villadsen, and her colleague J. Sebastian Pineda detected a repeating radio signal coming from YZ Ceti. The signal was recorded at a frequency of 2 to 4 gigahertz. It appears to be modulated by the rotation of the star and the orbit of YZ Ceti b, indicating an interaction between the star and the magnetic field of the planet. This discovery could have major implications for our understanding of exoplanets and their magnetic fields. Although YZ Ceti b is unlikely to be teeming with life due to its close proximity to its star, the detection of its magnetic field is important because it provides a method for discovering more life-friendly worlds in the future. But what does this signal really mean? And why are magnetic fields so important in our search for life? To answer these questions, we need to look deeper into the invisible force fields that shape our universe. Magnetic fields are a fundamental force of nature. They guide the hand of the compass, help birds navigate their long migration, and protect our planet from the harsh solar wind. But magnetic fields are not just an earthly phenomenon. They also play an important role beyond the Earth. Our Sun, for example, has a complex and dynamic magnetic field. It controls the Sun's activity from the formation of sunspots to the eruption of solar flares. Magnetic fields also shape the structure of galaxies, directing the movement of interstellar gas and influencing the formation of new stars. But perhaps the most intriguing role of magnetic fields in space is their potential impact on planetary habitability. A strong magnetic field can protect a planet from harmful radiation from its star, helping to maintain a stable atmosphere, and perhaps even conditions suitable for life. That's why it's so interesting to detect a potential magnetic field on exoplanet YZ Ceti b. This could provide valuable information about the planet's atmosphere and its potential to support life. How do magnetic fields affect the detection and interpretation of signals from space? To understand this, we need to delve a little deeper into the nature of radio signals and magnetic fields. Radio signals are a type of electromagnetic wave, which means they are composed of oscillating electric and magnetic fields. These fields can interact with other magnetic fields they encounter as they travel through space. When a radio signal passes through a magnetic field, it can be altered in various ways. Its direction can be changed, a phenomenon known as deflection. Its polarization, or the orientation of its electric field, can be rotated. Its frequency, in other words, the number of waves passing through a point in a given time, can be shifted. These changes can provide valuable information about the magnetic field that caused them. By studying these changes, scientists can infer properties of the magnetic field such as its strength and orientation. But magnetic fields can also pose problems for detecting signals from space. They can cause interference, making it difficult to detect the signal. They can distort the signal, making it difficult to interpret. This is why the study of magnetic fields is so important in the field of radio astronomy. By understanding how magnetic fields affect radio signals, scientists can develop methods to correct these effects and extract valuable information hidden in signals from space. To better understand the influence of magnetic fields in creating favorable conditions for life on the planet, let's turn our gaze closer to home, to a familiar red-headed neighbor in our cosmic backyard. Mars, the red planet, has long captured our imagination. With its towering volcanoes, deep canyons, and hints of liquid water, it is one of the most intriguing places in our solar system. But Mars also presents us with a mystery. Unlike Earth, Mars has a very weak and inhomogeneous magnetic field. This has serious implications for the planet's atmosphere and its ability to support life. Mars' magnetic field is not created by a dynamo in its core like Earth's. Instead, it's the remnants of magnetism trapped in the planet's crust from the time when Mars actually had a global magnetic field. Without a strong magnetic field protecting it, Mars's atmosphere is directly exposed to the solar wind, a stream of charged particles emitted by the sun. Moreover, new models presented by R. Sakata of the University of Tokyo and others suggest that a weak magnetic field like Mars after its dynamo is turned off could actually lead to a more rapid loss of atmosphere than if there were no magnetic field at all. Modeling has shown that a weak magnetic field results in the fastest rate of atmospheric ion loss, 6 times faster than without a magnetic field. The reason is that the weak magnetic field strength lines were easily repelled by the solar wind, creating a path for ions to escape into space over the night side of Mars. This suggests that Mars' remaining magnetic field may have hastened the planet's transformation into the cold and barren world it is today. Over billions of years, this caused Mars to lose much of its atmosphere, a process known as atmospheric stripping. This turned Mars from a potentially warm and wet world in its early history into the cold and dry planet we see today. The case of Mars provides a vivid illustration of the importance of magnetic fields to a planet's habitability. It shows us that without a strong magnetic field, a planet, even one as Earth-like as Mars, can lose the things that make it habitable: atmosphere and water. By the way, we've already looked at the problems and potential solutions to make Mars a second home for humanity in a separate video. Exoplanets, planets orbiting stars outside our solar system, have recently become a major focus of astronomical research. With more than 1,000 discovered to date, they offer a wealth of opportunities to learn about the diversity of the planetary systems in our galaxy. One of the most exciting developments in this field was the discovery of the first known magnetic field on an exoplanet in late December 2021 by an international team of astronomers who used the Hubble Space Telescope for their research. It was discovered on a Neptune-sized planet called HAT-P-11b. HAT-P-11b is located about 123 light-years away in the constellation of Swan. It is a hot Neptune, a type of exoplanet that's similar in size to Neptune, but much closer to its star, resulting in high temperatures on the planet's surface. The detection of a magnetic field on HAT-P-11b was a groundbreaking discovery. It showed that exoplanets can generate magnetic fields just like planets in our solar system. As we mentioned earlier, studying the magnetic fields of exoplanets can provide valuable information about their internal structure, atmospheric properties, and potential habitability. For example, a strong magnetic field can protect a planet's atmosphere from stellar winds, helping to preserve conditions that could support life. That brings us back to YZ Ceti b, an exoplanet from which a signal was recently detected. If this signal is indeed indicative of a magnetic field, it could have a major implication for our understanding of this exoplanet and its potential for life. Traveling through space from the familiar landscapes of Mars to the far reaches of YZ Ceti, we've truly come to realize the invisible power of magnetic fields, the profound effect on planets, and their potential to harbor life on them. The field of studying signals from other galaxies has grown rapidly over the past few years. For example, the Giant Metro-Wave Telescope in India has detected a faint signal from the most distant galaxy to date. The signal detected by YZ Ceti opened another new window into the universe, reminding us how much we still have to learn about our world. As we look to the future, the study of signals from other galaxies will continue to be the focus of space research. Each signal carries the potential for new discoveries. So when we look up at the night sky, let's remember that we're not just looking at stars and galaxies. We're looking at a universe filled with unseen forces, whispered signals, and hidden possibilities. And as we continue to listen and explore, who knows what we might discover next? In the vastness of our system lurks a considerable mystery, a source of energy and life, our sun. For a decade, the Space Guardian, NASA's Solar Dynamics Observatory, has been our unblinking eye on this fiery giant. This mission, launched into space February 11, 2010, set out on an odyssey not just to observe, but to unravel the mysteries of our nearest star. Imagine a world where a single second reveals a story millions of years old, where plumes of fire burst from the surface of the sun, larger than the Earth itself. It's a world that explores SDO, a world where every 3/4 of a second a new image is captured, each one a piece of the puzzle in understanding the sun's impact on our solar system. As we venture through a decade of solar observations, we're immersed in a realm where colossal waves ripple across the sun's surface, where plasma eruptions challenge our understanding of physics, and where the solar cycle resonates throughout the solar system. This is not just a journey of a satellite and a star. It is a story of discovery, the challenges faced, and overcoming them. Our journey with the Solar Dynamics Observatory begins with a momentous event: launch. February 11, 2010. Amidst the roar of the engines and the fiery takeoff of the Atlas V rocket, SDO begins its mission to explore the mysteries of the Sun. This launch marked not only the beginning of the mission, but also the beginning of a new era in solar observations. Once in space, SDO moved into geostationary orbit, positioned to have an unobstructed view of the Sun. Its main goal? To understand the Sun's influence on Earth and the solar system by studying the solar atmosphere in unprecedented detail. Central to this mission is a suite of sophisticated instruments aboard SDO, each designed to study different aspects of the Sun's behavior. Prominent among them is the Atmospheric Imaging Assembly. This remarkable instrument takes images of the solar atmosphere at different wavelengths, each revealing different features of the Sun. The capabilities of the AIA are truly revolutionary. It observes the Sun in 10 different wavelengths, each tuned to a specific temperature of solar material. This allows scientists to see the Sun's surface and atmosphere in a spectrum of colors, with each color revealing unique phenomena. AIA's observations have been instrumental in advancing our understanding of solar dynamics, from cooler and darker sunspots to blazing hot coronal loops. Over the past decade, it's tirelessly observed the Sun, taking more than 425 million high-resolution images, each image contributing to a continuous stream of data, painting a vivid portrait of the Sun's dynamic behavior. Why do we study the Sun so diligently? The answer lies in the Sun's profound influence on our system. It is the heart of our cosmic environment, controlling processes from polar lights on Earth to weather patterns on other planets. Understanding the Sun means understanding the fundamental processes that govern our corner of the universe. Through the eyes of the AIA, we witness the story of the Sun unfold in real time. Ejections of solar material, twisting magnetic fields, and the intricate dance of solar flares have all been captured in stunning detail. The AIA didn't just open a window into the Sun's activity, it paved the way to understanding the complex interactions that drive solar weather. This decade-long observation has revealed the dynamic nature of the Sun in unprecedented detail. From the ebb and flow of solar flares to the mysterious 11-year solar cycle, SDO has provided insight into phenomena that was once mere speculation. The mission has witnessed previously unfathomable solar events. Across the vast expanse of space, the Solar Dynamics Observatory plays the role of a vigilant observer, capturing every nuance of the Sun with unprecedented precision. Over its decade-long operation, SDO has amassed a stunning collection of more than 425 million high-resolution images, creating a continuous image of the Sun's ever-changing face. Imagine a world in which every fraction of a second reveals a new aspect of our star. SDO operates in such a mode, acquiring images of the Sun every 0.75 seconds. This relentless pace of observation allows us to see the dynamic nature of the Sun in real time, capturing processes and changes that were once beyond our view. SDO's ability to observe the Sun at different wavelengths has opened up new possibilities for understanding our star. Each wavelength reveals a unique layer of the Sun's atmosphere, from its turbulent surface to the outer limits of its corona. This multi-wavelength approach allows us to see the Sun in all its manifestations. Among the wavelengths that SDO observes, one that stands out is the extreme ultraviolet wavelength of 17.1 nanometers. This particular wavelength gives us a unique view of the solar corona, the outermost part of its atmosphere. The corona is a hotbed of solar activity where temperatures reach millions of degrees and where the mysteries of solar phenomena such as coronal mass ejections and solar flares lie. Through the SDO prism, the corona is no longer a dark region, but a bright, dynamic environment. We see coronal loops, giant arcs of plasma driven by the sun's magnetic field, and witness eruptions that send waves of solar material into space. These observations are not just visually stunning. They are key in helping us understand how the sun affects space weather and, in turn, our own planet. As we continue to explore the sun with SDO, every image and observation at every wavelength adds to our understanding of our star's enigmatic corona, revealing a dynamic and complex celestial body like never before. By embarking on a quest to decipher the 11-year solar cycle, the Solar Dynamics Observatory has been at the forefront of solar science. This cycle, a rhythm that's puzzled astronomers for years, is characterized by periodic changes in the sun's activity, including the frequency of sunspots, solar flares, and coronal mass ejections. SDO's decade-long observations cover nearly a full solar cycle, offering a front-row view of the sun's changing dynamics. During periods of solar maximum, the sun is a swarm of activity, teeming with sunspots and erupting with intense solar flares. Conversely, during solar minimum, the sun enters a quieter phase with fewer sunspots and less surface activity. Throughout its mission, SDO has witnessed and meticulously recorded many solar events. Incredible eruptions of plasma known as coronal mass ejections have been captured in detail, revealing the enormous energy released as these events unfold. Solar flares and intense bursts of radiation have been observed in different wavelength ranges, providing insight into the mechanisms that trigger these explosive events. In addition to this spectacle, SDO has also observed rare and mesmerizing passages of planets along the sun's surface. These events, while exciting in their own right, serve a more important purpose in solar science. They offer unique opportunities to study the sun's atmosphere and its interactions with celestial bodies, further expanding our understanding of solar dynamics. In space exploration, challenges are as inevitable as they are varied. NASA's Solar Dynamics Observatory has faced its fair share of obstacles, each of which has tested the mission's resilience and ingenuity. From Earth shadows and lunar eclipses to technical obstacles, such as the Atmospheric Imaging Assembly instrument problem in 2016, SDO's path has been thorny and winding. One of the persistent problems SDO faces is eclipses caused by the Earth and Moon. These celestial landmarks, although a natural part of the orbital path, temporarily limit SDO's ability to observe the sun. Earth eclipses occurring on equinoxes cast a shadow over the observatory, resulting in short periods of darkness and interrupted data transmission. Similarly, lunar transits, although rarer, momentarily block SDO's view of the sun, creating a unique but challenging scenario for solar observing. In 2016, SDO faced a major challenge when its key instrument, the Atmospheric Imaging Assembly, encountered technical difficulties. This failure jeopardized one of the mission's most important data streams. The AIA, responsible for high-resolution imaging of the solar atmosphere, is integral to understanding the sun's dynamic behavior. The problem with AIA was complex and revolved around the problem of detecting and analyzing invisible coronal mass ejections. These CMEs, which occur at high altitudes in the solar corona and regions with weaker magnetic fields, are notoriously difficult to observe. Unlike typical CMEs, which appear as visible dimmings or brightenings on the sun, hidden CMEs can often be detected only with special instruments like a chronograph. Solving the AIA problem required a coordinated effort between engineers and scientists. The team applied new techniques to visualize the remote sensing data acquired by the AIA by comparing different images, current images of the sun with images taken 12 hours earlier. The team was able to capture slow changes in the lower part of the corona. This method revealed subtle, previously overlooked changes in the sun's magnetic fields and plasma loops. Advanced image processing techniques, including wavelet packet equalization and multi-scale Gaussian normalization, were applied to improve the visibility of these subtle changes. These techniques allowed the team to detect dimmings and brightenings in the sun's disk associated with hidden CMEs, which was a breakthrough in solar observation. Successfully addressing these changes not only allowed the mission to continue, but also enriched our understanding of what it takes to sustain a long-term space observatory. As we delve deeper into the implications of the Solar Dynamics Observatory findings, we discover the sun's profound influence not only on Earth, but also on the broader expanse of space. Decades of SDO observations have greatly advanced our understanding of space weather and its many implications for our planet and beyond. Space weather, the term for the energetic activity of the sun, includes phenomena like solar flares, coronal mass ejections, and solar energetic particles. These events, born from the sun's dynamic surface and atmosphere, can propagate through space, affecting both planets and spacecraft. When it comes to Earth, the effects of space weather are both interesting and far-reaching. The interaction of solar wind and coronal mass ejections with Earth's magnetosphere can lead to spectacular auroras, commonly known as the northern and southern lights. However, these interactions can also have more devastating consequences, such as disruptions to satellites, communication systems, and even power grids. The SDO findings have played a significant role in enhancing our ability to predict space weather events. By understanding the mechanisms that cause solar eruptions and their trajectories, scientists can better predict when and how these events might affect Earth. Such prediction is critical to preparing and protecting our technological infrastructure in space and on the ground. Beyond Earth, the implications of SDO research extend throughout the solar system. Understanding space weather is vital to the safety of astronauts in space and to the planning and execution of interplanetary missions. As we venture deeper into space, whether the Moon, Mars, or beyond, knowledge of the sun's behavior becomes increasingly important. To summarize, the implications of a decade of SDO observations are profound and far-reaching. This mission's not only deepened our understanding of space weather and its impact on Earth, but it has laid the groundwork for safer space exploration for coming decades. As we look into the future of solar observations, the horizon is full of hope and potential. The current era of solar exploration is marked by groundbreaking missions such as the Parker Solar Probe and Solar Orbiter. The Parker Solar Probe, launched in 2018, has already come closer to the Sun than any spacecraft ever before, and will eventually dive into the corona to tell us about its mysteries. The Solar Orbiter, the product of a collaboration between ESA and NASA, launched in 2020, and it's equipped to provide a comprehensive view of the Sun's poles and its outer atmosphere, previously unexplored regions. These missions are equipped with state-of-the-art instruments designed to study the Sun in new ways. The Parker Solar Probe's journey through the solar corona promises insight into fundamental processes that govern the solar wind and solar energetic particles. The Solar Orbiter's unique orbit and extensive suite of instruments will provide a holistic view of the Sun's atmosphere, magnetic field, and solar wind. Looking ahead, the future of solar observation has brilliant potential. The opportunities for new discoveries are as vast as the Sun itself. We can unlock the secrets of the Sun's magnetic field dynamics, leading to a better understanding of solar flares and coronal mass ejections. Studying the Sun's inner workings could reveal more about the workings of its 11-year solar cycle. As we continue to observe and study the Sun, we stand on the threshold of a new era in solar science that promises to illuminate the darkest corners of our understanding of the star that sustains life here on Earth. In a world where gravity is taken for granted, we decided to unravel the hidden truths that lie behind the scenes. Get ready for us to delve into the mysteries that defy our understanding. What if the essence of gravity as we know it is nothing but an illusion? Today, we will dare to challenge everything you think is true. Together, we'll penetrate the veils of perception and uncover the mysterious secrets hidden at the very core of the fundamental principles of gravity. In the 17th century, according to a very popular legend, Newton was watching an apple fall in an orchard. He noticed the apple fell exclusively downward, as if under the influence of a certain force, which inspired him to create the universal law of gravitation. What does this law describe? A conventional apple gains speed as it falls. The apple, like everything else on the planet, has a mass, but it's much less than the mass of the Earth. According to Newton, the force of attraction between the Earth and the apple directly depends on their masses and is inversely proportional to the square of the distance between them. To make it even shorter, all objects with mass and energy are attracted to each other and are in a state of free fall in relation to more massive bodies. This is all expressed in a well-known formula. The formula is broken down as gravitational force, the mass of the primary, mass of the secondary, divided by the orbital radius squared. By the way, Newton tried to model gravity as a field that surrounds all material bodies. This mental model is still used to explain the gravitational interaction between all objects. According to Newton's third law of motion, the Earth should also move toward the apple since it also has its own field. But it's very small and we cannot feel it, which can be explained by Newton's second law, F equal ma, since it's impossible to get the same acceleration for objects with different masses even with the same applied force. However, it was not all bad news. Newton suggested that gravitational force may also affect space bodies, including the Moon. In addition, the satellite has not yet fallen to the Earth's surface, not only because of its constant rapid orbital motion, but also because of the gravitational interaction, which is less between massive objects located at a considerable distance from each other. Newton was able to explain the dependence of the planet's rotation around the Sun due to the gravitational force between them with an imaginary experiment. If you put a cannon on a mountain and shoot a cannonball horizontally, it will fall vertically to the Earth after flying a short distance. But if you shoot it with a very high force, for example, up to 4,500 miles per hour, the cannonball will always be in a state of free fall and will not reach the surface. According to Isaac Newton, this is the state in which our Moon, and in particular all other planets, even outside the solar system, are located. This is how Newton came to the conclusion that gravity is a universal force for the entire universe, acting in the same way everywhere. Moreover, Newton's law did not contradict but complemented other relevant laws. For example, the three laws developed by Johannes Kepler, they explain the movement of planets in outer space. The law of gravitation can be derived from each of Kepler's laws. Thus, according to Kepler's first and second laws, the orbit of each planet around a star is an ellipse, which means the distance to the planet to the star is constantly changing, including at the closest point from the planet to the Earth, perihelion, and the farthest point, aphelion, where the planet travels the same distance in the same time. Newton's law describes the acceleration of massive objects with respect to the distance to the star. In particular, the third law, which explains that an increase in the orbital radius affects the period of rotation, is also explained in the same way. Moreover, the force that keeps the planets in orbit is proportional to the product of the masses of the Sun and the planet and inversely proportional to the square of the distance between the two space bodies, just as it is between objects on Earth. However, Newton's law could not explain several important scientific observations. For example, Newton's theory explained the motion of the planets around the Sun well, except for one, Mercury. You may remember that Mercury has a strange oval orbit, but that's not the strangest thing. Its closest point of convergence is always in different places and moves slowly around the Sun. This process is called precession. Although this phenomenon is characteristic of all planetary orbits, it's most obvious and surprising in Mercury. The precession of Mercury's orbit is 5,600 angular seconds per 100 years when observed from Earth, but the actual precession time of the planet is 5,557 seconds. Now, those lost 43 seconds cannot be explained by Newton's theory. However, all of this and much more can be confirmed by another theory that is considered fundamental to modern science, Albert Einstein's general relativity. Almost 300 years after Newton's revolutionary discovery, Einstein introduced the world to his view of the concept of gravity in the general theory of relativity. GR was preceded by the special theory, in which Einstein described that space and time should be perceived as an inseparable phenomenon, such as absolutely everything in the universe moves simultaneously in time and space. According to GR, he explained that massive objects are capable of curving time and thus affecting other objects around them, and this curvature is gravity. While Newton's theory was based on a falling apple, Einstein imagined a person in a falling elevator to explain his idea. As he falls, he doesn't feel his weight, because both his body and the elevator are falling at the same speed. However, when the person is moving up in the elevator, he feels accelerated, and it seems that the floor is resting on him. However, if there are no windows in the elevator, then the person will not be able to tell what he or she is experiencing from his or her point of reference. Falling in a gravitational field or moving at a constant speed in a small region of time. In Einstein's theory, this is called the principle of equivalence. In fact, if according to Newton's law, a person falls down due to gravitational force, then according to Einstein's theory, it's due to the absence of a force that pushed the person up. That is, a person is affected by the force generated by the elevator floor, but it is not gravity. This also implies that we are always in a state of acceleration unless we're in a state of free fall or inertial motion from our point of reference. So then Einstein concluded that gravity and acceleration are one and the same, and therefore we're in a state of free fall until an obstacle appears in our path, which became the basis for understanding that gravity is not a force. This is a very unexpected statement. Let's take a closer look at the theory of relativity. So as we've already noted, according to Einstein, gravity is a geometric curvature of a four-dimensional time-space. Its property is not a force acting in space. One can simplistically try to imagine time as a two-dimensional drawn fabric in which massive objects like the planet and sun create funnels, but this is not quite the right idea. A better option is to imagine time as a three-dimensional grid consisting of lines geodesics along which planets move in free fall. They are massive enough to distort the lines along which any objects move. That is why it may seem to us that, for example, cosmic bodies are attracted to each other. The theoretical physicist John Wheeler explained this idea quite simply. Space-time tells matter how to move, matter tells space-time how to curve. We can't see the curvature directly, but we can see the effect of Einstein's gravity. For example, if the crew on the ISS is flying right next to the Earth, they will move in a circle due to the curvature, although from their perspective it will seem they are moving straight. But a large object prevents them from moving in lines. Furthermore, we can observe this on Earth. If two people move from a considerable distance to the North Pole, they will meet as they approach it. No force would act on them. They would simply follow curved lines due to the sphericity of the Earth. Same is true for light. Newton assumed that light is also bent by the gravitational force of massive bodies like all other objects, so the actual location of a light source like a star is different from what we see. However, modern science knows that light has no mass, so how could it be affected by large cosmic bodies? Einstein in turn expanded that light, like you and I, it moves along the same lines of geodesy. Since according to GR, the lines around heavy objects are deformed, light changes its course, meaning gravity does not act on the light itself. However, Einstein's calculations proved that the angle of light deflection was almost twice as large as according to Newton. Einstein's idea was confirmed by astronomers Arthur Eddington and Charles Davidson while observing a solar eclipse in 1919. They compared the actual location of the stars with the light captured in the photographs and were able to confirm that the angular deviation is indeed approximately 1.75 angular seconds as calculated by Albert Einstein. In particular, GR can also answer the question about the strange orbit of Mercury, since according to its calculations, the planet's orbit is shifted by 43 angular seconds due to the curvature of space. In addition, another proof that gravity is a curvature of time is that a wave of light can lengthen and lose its intensity due to the influence of massive bodies. So if an observer is in an accelerating spacecraft, then in his eyes the wave of light emitted from the bottom point would be elongated relative to its original wavelength. This in turn would cause the color of the light to change from red to blue. This phenomenon is called the redshift of light and is not predicted by Newtonian gravity. In 2016, Professor Andrea Ghez led a team of researchers to observe the blue star SO-2, which came close to the black hole Sagittarius A. If Einstein's theory is correct, then the light wave from the star should have changed its color to red for the scientist's reference point. And the star did indeed glow red, which again confirmed Einstein's gravity. So Einstein's gravity model has made a real breakthrough in understanding the physical process taking place in our universe. At present, it is confirmed by perhaps not all tests of its reliability and reveals many details of time-space. Nevertheless, the Newtonian model can still be a serious competitor for GR. For example, while observing the rotation of disk galaxies in the 1930s, Danish astronomer Jan Oort first noticed that the rotation speed of stars on the edge of such galaxies remains constant, although they should be moving much slower. The solution to this paradox is the hypothetical dark matter first described by astronomer Fritz Zwicky, which surrounds galaxies. According to current estimates, about 70% of the universe consists of 27% dark matter and 5% ordinary matter. However, although dark matter is an important hypothesis for explaining this phenomenon and many others, such as bullet clusters, Its existence has not been precisely confirmed so far. On the other hand, a modified model of Newtonian gravity, modified Newton dynamics, proposed by astrophysicist Mordecai Milgrom, can explain the orbital rotation state. There are other rules for objects with much lower acceleration than in our system. Milgrom modified the formula of gravity by adding the constant AO, which defines the critical point for acceleration. So if the acceleration caused by gravity reaches this point, then Newton's laws, which were in effect before the critical moment, will be replaced by the new laws introduced by GR, and the inverse square law that we observe in our solar system would stop working, which will equalize the acceleration, meaning it will not depend on the distance from the center. This theory, in fact, explains the motion of stars and many other galaxies without the presence of dark matter. However, it has several serious problems. For example, it cannot completely exclude the presence of dark particles, since galaxy clusters in the Mond analysis are still characterized by the problem of insufficient mass, which is solved by dark matter. Therefore, this theory, although it offers an explanation for the orbital velocity phenomenon, has, in particular, drawbacks that are still being solved by GR. And finally, the main problem with Einstein's gravity is the inconsistency with quantum mechanics. The main problem between these fields of physics is that GR is based on the principle of causality, while quantum physics is based on probability. Therefore, GR cannot work at the level of quanta, and quantum mechanics cannot work at the level of macroscopic objects, since an observer will know where a large physical object is located and how fast it's moving. There's no superposition state for it. The only solution to this problem can only be to develop a new theory of quantum gravity that would explain the interaction of objects and fundamental particles simultaneously. Despite some problematic issues, Einstein's repeatedly confirmed gravitational model is still the basis for modern research, regardless of its age. We cannot say whether GR will suffer the same fate as the law of gravity, but the coordination of the model of the world according to the theory, along with other areas of physics, is necessary without understatement for the whole of science. So since we do not yet have a new gravitational theory, we can summarize with some confidence that gravity is not a force. The observable universe spans 93 billion light-years, a distance beyond our comprehension. In this cosmic space are more than 2 trillion galaxies, each teeming with billions of stars. The scale of the universe is a marvel, but it is not just its size that fascinates us, it is its complexity. The cosmic web, a network of galaxies and dark matter, forms a structure that resembles a vast, interconnected network. Now let's travel to a place equally complex and impressive, the human brain. Composed of some 86 billion neurons, each neuron in the brain is connected to thousands of other neurons, forming a network of unprecedented complexity. The striking similarities between the cosmic web and neural networks are more than a poetic metaphor. It's a scientific curiosity that's led researchers to explore the quantitative similarities between the two systems. Could it be that the universe with its billions of galaxies is reflected in the complex neural networks of our brains? Are we, in some deep sense, a reflection of the cosmos itself? Could it be that the great design of the universe is reflected in the very essence of our being? Do the laws that govern the stars also govern the complex dance of neurons in our minds? These questions, once the domain of philosophers, are now being explored by scientists who are uncovering a connection that may be the key to understanding not only the universe, but also ourselves. Since the dawn of human consciousness, we've been attracted to patterns. The first humans looked up at the night sky, recognizing constellations and tracing the predictable movement of celestial bodies. They observed the cycles of the moon, the changing seasons, and the complex symmetry of leaves and shells. This innate ability to find patterns in nature is not just curiosity. It's a fundamental aspect of our intelligence, the way we understand the world around us. As we evolved, our understanding of patterns changed. We began to realize that these patterns were not simple coincidences, but were governed by fundamental principles and laws. The ancient Greeks discovered the golden ratio, a mathematic constant found in architecture, art, and even the human body. Mathematicians such as Fibonacci discovered sequences that describe the growth patterns of plants and the spiral motion of galaxies. Natural patterns are not limited to static shapes and numbers. They are dynamic, unfolding in time and space. The branching of a tree, the winding course of a river, the swirling of clouds. Everything is subject to mathematical patterns and fractal geometry. These patterns are self-similar. That is, they look the same at any scale, whether you're looking at a single leaf or an entire forest. In the modern age, our search for patterns has led to revolutionary discoveries. The double helical structure of DNA, the strange world of quantum physics, and the butterfly effect and chaos theory all reveal a universe governed by patterns and laws. These discoveries have not only expanded our understanding of the universe, but have also shaped our technology, medicine, and philosophy. But what drives this relentless search for patterns? Is it simply a survival tool, or does it hint at a deeper connection between us and the cosmos? Could our ability to recognize patterns be a reflection of the inner order of the universe, a cosmic signature imprinted in our very being? In a field of scientific research where the mysteries of the cosmos meet the riddles of the human mind, the research of Franco Vazza and Alberto Folletti serve as a beacon of innovation. Their pioneering work has opened new doors in our understanding of the universe and neural networks, revealing striking similarities that challenge our very perception of reality. At the heart of their research is a question that's intrigued scientists and philosophers alike. Is there a connection between the structure of the universe and the neural networks in our brains? Vazza and Folletti have plunged headlong into exploring this question using cutting-edge technology and mathematical models. Their approach was quite quantitative and focused on the distribution of matter in the cosmic web and the connections between brain neurons. By analyzing large data sets and applying advanced algorithms, they found that the structure of the universe and neural networks obey a similar pattern known as degree distribution. A staggered distribution is a mathematical relationship in which a small number of nodes have many links and most have only a few links. This pattern is found in a variety of natural phenomena, from the internet to social networks. Vazza and Folletti found that the same pattern exists in both the cosmic web and the neural networks of the brain. The implications of this discovery are profound. It suggests that the universe and the human brain share a common architecture, a universal structure that transcends scale and complexity. This connection is not just a poetic metaphor, but a scientific reality, a cosmic signature that resonates in the very fabric of existence. The innovative research of Franco Vazza and Alberto Folletti has ignited a spark in the scientific community. Their discovery of structural similarities between the universe and neural networks has opened new doors, leading to a lively dialogue among experts. Dr. Alberto Folletti commented, "Our study is just the beginning of a longer story. We have shown quantitative similarities between these two systems in structural terms. The architectures of these complex networks look strikingly similar. Combining the efforts of neurobiology and astrophysics can expand our ability to get more results." The significance of their findings goes beyond mere academic curiosity. From understanding dark energy to the development of artificial intelligence, the potential applications are enormous. Dr. Alberto Folletti also added, "If we can demonstrate the similarities between a network such as a neural network and the structure of the universe, we may be able to gain more detailed information about the universe and galaxies. This merging of analysis tools from two different disciplines may help in accelerating the process of developing artificial intelligence or artificial neural networks. But the study has also sparked reactions outside the scientific community. Some have used the results to justify creationist theories or New Age viewpoints. Vasa and Folletti clearly emphasized that their work is based on scientific research and has nothing to do with creationist theories or metaphysics. The future of this research is filled with hope and curiosity. Both researchers express a desire to continue exploring this area by looking deeper into the comparison of these two complex systems. They believe that these results need to be analyzed with more sophisticated tools and that the next steps involve moving to a higher level of complexity comparison. As we delve into the mysteries of the mind and the cosmos, we enter a paradox that has both fascinated and puzzled thinkers for generations. In the vast expanse of the universe, where time and space stretch beyond comprehension, lies a paradox that has baffled philosophers and scientists alike: the paradox of Boltzmann's brain. This paradox is named after 19th century physicist Ludwig Boltzmann, and it delves into the very nature of reality and our understanding of consciousness. Boltzmann's original idea was rooted in statistical mechanics, which studied the probability of random fluctuations in a system. Imagine a universe filled with chaos where particles are in constant motion. In this chaos, there's negligible chance that the particles could randomly line up and form a self-conscious brain. This brain, existing for a fleeting moment, would have thoughts, memories, and perceptions of reality, all without a body or a world to live in. The paradox arises when we take into account the vastness of the universe and an infinite amount of time. Given enough time, the random formation of such a brain becomes not just possible, but inevitable. This leads to the unsettling conclusion that it's more likely for a solitary, self-aware brain to exist in the void than for our entire observed universe to have evolved it as it has. The implications of the Boltzmann brain paradox are profound and disturbing. If the existence of such a brain is more likely than the existence of our universe, what does this say about our reality? Are our perceptions and experiences merely illusions? Are we too just momentary fluctuations of cosmic chaos? The paradox has sparked debate and reflection among philosophers, scientists, and thinkers. Some see it as a challenge to our understanding of probability and the nature of existence. Others see it as a metaphorical exploration of solipsism, the philosophical idea that only the mind of man necessarily exists. From Boltzmann's enigmatic brain paradox, we venture further into the uncharted territories of consciousness. The question that has intrigued scientists and philosophers alike is whether the universe itself can be conscious. The idea that the universe may possess consciousness is not new. This concept has been explored in various philosophical traditions and resonated in some scientific theories. Historically, the concept of a conscious universe has been associated with panpsychism, the philosophical view that all things possess consciousness. This idea has been adopted by some Eastern and Western philosophical traditions, suggesting that consciousness is a fundamental aspect of reality. In the realm of science, theories suggesting that the universe may possess consciousness have emerged from the study of quantum mechanics. Some interpretations of quantum theory suggest that consciousness plays a role in the collapse of the wave function, implying that the observer and the observed are interconnected. Cosmologists and neurobiologists have also explored this concept to understand how consciousness might manifest itself on a cosmic scale. Theories such as integrated information theory, or IIT, suggest that systems with a high degree of complexity and integration may possess consciousness. This leads to the tantalizing possibility that the universe, with its complex web of galaxies and cosmic structures, may have a form of consciousness. The idea of a conscious universe is still a subject of debate and research, yet it's firmly planted in the realm of speculation. Although it encourages us to think about our place in the cosmos and the interconnectedness of all things, the idea enters metaphysical territory and should therefore be treated with caution and critical thinking. Having considered speculative ideas of a conscious universe, we turn our attention to a more grounded and scientific theory, the fundamental theory of consciousness of Donald Goffman. Dr. Donald Goffman, a renowned neuroscientist and philosopher, has devoted his life to unraveling the mysteries of consciousness. His groundbreaking theory seeks to explain one of the most mysterious phenomena in existence, the nature of conscious awareness. Goffman's theory is built on the premise that consciousness is not simply a byproduct of complex computations in the brain. Instead, he argues that consciousness is a fundamental aspect of reality akin to space and time. Drawing on quantum mechanics, neurobiology, and philosophy, Goffman's theory explores the interplay between micro and macro levels of existence. He suggests that consciousness arises from the complex interactions of quantum particles within the brain, governed by principles beyond traditional physics. Goffman's work has led to new experiments and collaborations across scientific disciplines. His theory's been tested through rigorous empirical research using advanced technology to explore the depths of consciousness. Although Goffman's theory has received the support and admiration of many in the scientific community, it has not been without controversy. Critics argue that the theory's reliance on quantum mechanics and its bold claims about the nature of reality require further confirmation and study. Nevertheless, Donald Goffman's fundamental theory of consciousness offers a new view of consciousness that bridges science and philosophy. The connections between the universe and neural networks go beyond mere scientific curiosity. They open the door to deep philosophical reflection and have broader implications for our understanding of existence. These connections invite us to see the universe not as a collection of isolated objects, but as an interconnected network of relationships. They inspire new ways of looking at technology, ethics, and our responsibilities as inhabitants of the cosmos. The study of the universe and consciousness has been a central theme of philosophy for millennia. From ancient Greek thinkers to modern philosophers, the quest to understand reality, existence, and our place in the universe has shaped human thinking. Some see the universe as a deterministic machine, while others take a more mystical view. The connections between the universe and the mind only add a new dimension to this age-old debate. The idea of interconnectedness is not just a scientific observation, it is a call to reflection. It invites us to see ourselves as part of a greater whole, realizing the delicate balance of life and the universe. It forces us to think beyond ourselves and consider the impact of our actions on the wider cosmos. The journey ahead promises exciting discoveries. While the connections between the universe and neural networks are fascinating, it's important to approach them with scientific rigor. Misinterpretations and sensationalism can lead to misunderstandings and detract from the true scientific value of these discoveries. So let our curiosity guide us in our explanation of the cosmos, and let our critical thinking help us stay grounded as we continue to explore the uncharted territories of understanding the universe.